It's awesome. It's complicated. It's beautiful. And it's infinitesimally small.
It's the biggest technology challenge since the information superhighway, engaging scientists, entrepreneurs and governments from Moscow to Melbourne. At briefings in Washington, in laboratories, seminars, workshops, public debates and conferences around the globe, from Sydney to Perth, New York to Tokyo, it is revolutionising science. Not visible to the naked eye, tiny self-assembling systems like these offer big solutions to some of the world's most complex problems. This is science on the nanoscale. For scientists, it's the biggest game in town. So what is nanotechnology?
Nanotechnology is like technology on a really small scale.
That's an interesting question.
Well, nano. Is nano small?
It's obviously small.
Small things for technology, I suppose. Yeah. I have an iPhone Nano.
Nanotechnology.
You'd have to ask him.
Very little. It's all about first getting tiny robots to do things for you.
Well, would nanotechnology be, because we're looking at buying an iPod?
No, it's nothing to do
It's
with
just nothing to do with iPods, where the tiny weeny little ones from iPods.
I don't know a great deal about nanotechnology. We're using it for doing things in the bloodstream and things like that.
It's the science of making things smaller, is it?
There's so much mystique about nanotechnology. 1 nanometer is 1/1000th of a metre, about the size of 6 carbon atoms, or slightly less than 1 water molecule. Almost too small to imagine. And nanotechnology is the science of interacting with atoms and molecules to modify the way they behave.
By chemically creating ferrofluids, for example, or liquid magnets that exhibit this bizarre spiking behaviour in response to external magnetic fields. Or by fabricating nanoscale semiconductor crystals known as quantum dots, sometimes called artificial atoms, that glow like Christmas lights. Or by waving the alchemist wand over very fine particles of gold in solution to modify their shape and size, effecting dramatic colour changes from yellow through deep blue to red, depending on the size of the nanoparticles.
Scientists have been modifying materials for decades. In fact, nanotechnology's been around since the early Romans. They use gold and silver nanoparticles to make really interesting colour combinations in glass. It's also about the technologies. Materials behave differently in the nano world, and scientists can now direct those behaviours to create new, phenomenal capabilities.
Like liquid electronics in your smartphone, embodying nanoparticles suspended in liquid that go where you want them to go. Capabilities like these, in the pipeline at RMIT University, herald a new generation of devices that will reassemble themselves at the touch of a keypad. Or nano-engineered nanowires, projecting material science into the new horizons of nano art glowing from your walls.
Most of us associate nano with iPods, but there are nanoparticles and processes all around us. In the natural world, and in the manufactured one. Nanotechnologists even exploit the strange properties of glass by using special coatings to change the way it behaves. So scientists, engineers and industry are now collaborating globally to bring these extraordinary nano capabilities into the material world.
This is a multi-million-dollar hub, a workshop where scientists and engineers from universities, industry, organisations like CSIRO from around Australia and even internationally come together to use nanotechnology and nanofabrication tools to solve real-world problems in health, in water, in energy, and even the next generation of consumer gadgets to build viable manufacturing industry in Australia.
Scientists have also recruited Nano to fight fraud. Scientists turn their skills here to writing with light, impregnating holograms into products like banknotes. These techniques are so sophisticated, they're incredibly difficult to counterfeit.
We call them optical anti-counterfeiting devices. Most of the people are familiar with it. So if you look at the device from one direction or another, you actually see different pictures coming out. The way these things are made is by using an electron beam lithography tool to create millions of tiny little shapes placed according to a specific design that will reflect light at different angles. So when you see the whole device, you actually get different pictures if you're looking at it at different angles.
Indeed, this dynamic coupling of new tools and technologies is moving so fast, it's possible to now routinely control the positions of atoms and molecules on surfaces.
Systems such as this one contain a tuning fork structure which is miniaturized. It's about 1 millimeter in size, embedded deep within a vacuum system. And these have been used to detect the forces required to actually push single atoms around. Using this tool, you can detect the force required to actually move an atom. You can also detect the force required to put single electrons on and off of that single atom.
So now we're pushing atoms around.
Imagine what we can create. Now we can visualise atoms and molecules. We can create tailored nanostructures. We can create special molecules. These might perhaps be used in next generation solar cells. Maybe they'll be used in next generation computers. We could even create a nanoparticle which could target individual cancer cells with the chemotherapy drug. We've got the chance to create special molecules which might be able to be used to clean water, or nanostructures that might be able to be used to remediate lands. The possibilities are really quite endless. Just imagine what we could do over the next 20 years.
It's Nanotechnology's designer solutions that will light up our future. Using photovoltaic energy that's cheaper than fossil fuel. Oil-gobbling robots to clean up our oceans. And minute medical robots to revolutionise complex surgery. The science behind devices like these begins where technology interacts with biology.
We can manipulate the nanostructure of material surfaces so as to control how they interact with their environment. We're seeking biocompatibility in these materials in order to make structures on which we can get living cells to regenerate. In this case, bone and cartilage cells in a badly injured knee. If we get the structures right, these cells migrate to the scaffold, settle and proliferate. They secrete proteins that self-assemble to fill up the pores. With bone, bone and cartilage, or cartilage.
What happened to the scaffold?
It degrades into harmless chemicals that the body excretes.
We also work with layers on nanoparticles to create smarter anti-cancer therapies. We encapsulate the drug so it doesn't degrade too quickly.
So the Y-shaped molecules are antibodies, and these can help target the capsules towards cancer cells and help them penetrate inside. So when the capsule hits the target, it degrades and releases the drug.
Yes, timing of drug release is critical, especially for applications in the brain. And we're developing implants for epilepsy detection and control. The idea is that electrodes within the implant will detect signals from an impending seizure and enable controlled drug delivery to act against that seizure.
The tricky bit's combining seizure detection with drug delivery, and in orthopaedics, having cell and cartilage growth in tandem in a fabricated environment.
So what does the future hold?
If we get it right, new freedom for people with epilepsy.
We can take regenerative medicine to a new level, enabling advances in nanotechnology to facilitate more effective bone, cartilage, nerve and muscle regeneration. We are at the initial stages of these exciting developments, but we are establishing a platform that can revolutionise these fields of medicine.
These are game-changing technologies. Not only are scientists working on applications for nanotechnology, they are also exploring ways to keep it safe for people and the environment.
The challenge is, how do we as a society keep these technologies safe?
Well, this is frontier science. Game-changing? Absolutely. But not without risk, nor without its critics, as our media often remind us.
Consumer groups are quite concerned about the ineffective or unregulated nature of nanomaterials in consumer products such as sunscreens, cosmetics, as well as food and food contact materials. They're also concerned about the eventuality of nanomaterials ending up in the environment. Their concerns are not unique. These concerns are shared by scientists, governments and government agencies. The potential implication of the technology is huge, but we can't allow it to develop and come onto the market without an effective regulatory framework to govern it.
A famous physicist once said, imagine you could arrange the atoms the way you want, the very atoms, all the way down. Well, now we can. When you take great leaps like this, you invite risk. And what you need to manage that risk is a global consensus. That's the way to go.